It's not a short lecture, right? And on top of all of it is going to be theory and logic and complexity, so it's going to be fun. But yeah, I hope to make it interesting to all of us. All right, so before I'll describe the structure of this lecture, I'll start with some motivation or context. Okay, so the main topic is text analysis or text analytics. And to get into the context of this talk, let's talk about a few of the applications that we're using the products of systems using text analysis or based on text analysis. So Renee was talking about search and information retrieval. I think this is one of the oldest traditional usage of text analysis, which is not just about building inverted indexes where you give it a word and you get a list of documents, but nowadays search engines are expecting to do much better. We expect them to understand the meaning of the query, to understand the meaning of a document or text or HTML, to understand how the two match together, and so on. This is also the case with specific domain search engines like Scholar when you're looking for papers, or search on social networks, search in the biological domain. I'll speak about it a little. And one of the ways that these search engines are intelligent is by using this concept of a knowledge graph, right? A knowledge graph, think of it as just a big database of some very generic, simple schema, a graph, basically, a graph with the labeled edges. And this whole movement of the semantic web and linked data essentially aims to encode all of the human knowledge in a computer-friendly format. Okay, so a lot of it is given in machine or human-friendly formats like text, Wikipedia, books, and the movement of the semantic web led by the W3 consortium, led by Tim Berners-Lee, is getting to this machine-friendly representation of this data. And again, one of the important applications of these knowledge graphs are in the life science domain. Now, in life sciences, in all of this biological, biomedical research or science, they really have an explosion of publications, of text. If you think of some repository like Medline, it has something like 30 million different papers on different findings in the biological domain or the medical domain. So if you want to read these publications and make the inference that if some medical condition causes the disease, so if a condition A causes disease B and disease B leads to a problem C, making the inference from A to C is really not a human kind of task. It is really a machine task. It's not a human intelligence, it's artificial intelligence. Okay, so there is more and more research and science around how to read these publications using machines. Right, a few more. So in the commercial domain, in the CRM, customer relationship management, companies are trying to find the sentiment and trends of clients against their products from, say, customer claims or customer reviews on the website. And yeah, companies with lots of customers, that becomes text analysis task. Another classic application is the comparison shopping, where you have these meta shopping websites that go over different websites trying to extract products and the prices and comparing between them, making suggestions. So this is not just text analysis, it's also HTML analysis. And okay, these applications also attach themselves frequently to email applications, trying to get information regarding the way you manage the relationship with the customers from your emails. Okay, so you have applications like this strict thing that goes into your email, right, if you choose to install it, and read something like, hey, it seems like there's a to-do here for you in this email, or you're expected to answer quickly, but you haven't replied to it for like a week. Are you behind on this email? So this is a notification. And of course, the usual stuff that we have going on with email services like auto-completion or automatic replies, or spelling correction. Spelling correction is no longer about just going and seeing that the word is not in the dictionary and finding a closest word, but getting more into the semantics of what's written and understanding it both grammatically and sometimes contextually. All right. Last but not least, applications are in the domain of social media. So social media, who cares about the text there? So it can be companies, commercial companies, looking for what are people looking for and what are the trends. And this can be political campaigns, trying to understand what is the impact of their campaign on people and where are the trends again and who are the key personnel that we should address and so on. But it also goes to the dark side of cyber crimes and cyber security, where you have a machine going and trying to find content in the social media that is actually criminal. Like ads for terror recruitments and ads that promote business around child exploitation, human trafficking. There's been some projects involving Stanford, I think, on trying to find ads that in effect promote human trafficking jobs, right? Like find an ad where there's a high-paying job in some exotic place without any clear required skills, right? So these are several, just representative of domains where there's a high motivation to do text analytics. Just to complete the pictures, the picture on that. So I was working at the IBM Research Lab in San Jose, Almaden, until the end of 2013. And there I was in the group that was building text analytics system T, that I'll talk about frequently in this lecture. And we were involved in two challenges there, or many challenges, but two of them are here. One was the Jeopardy challenge, where basically this Watson machine was competing against the human contestants, and it beat them to a large extent, right? Big time. How did it use it? Well, there are basically two main challenges. One was to build a large knowledge graph that was stored in the machine, and the other one was understanding what the question is asking. There was also the challenge of matching between the two, mapping between the what the question is asking and what the knowledge graph has. Well, what was this knowledge graph containing? A lot of the content was information that was extracted from text. It was either Wikipedia or books or content of Yago, which by itself is extracted from Wikipedia text. All right? And another challenge was this collaboration with, it's called the Baylor team, where we had algorithms reading a specific subset of Medline papers. And these were about studies of some specific protein called P53, which has the role of causing a cell to terminate. It's kind of in charge of the tumor suppression. So it's considered an important protein in the study and the treatment of cancer. So this study was basically looking for other chemical, biological entities that were interacting with this P53 and stimulating it, turning it on. All right? So it was considered a success. It got to do some nice things in a short amount of time compared to the actual human hours that were or human years that were invested in these kinds of problems before that. Okay, so in this text analytics, core problem, a central problem, is what we refer to as information extraction, which is, an abstract term that refers to every task of taking data that is hidden in text and moving it to a structured format, right? Data in the text, move to data in the database, which has its schemas and attributes and so on. Okay, so you can find a lot of definitions out there on information extraction, but the kind of usual definition looks like has this structure of a process that selectively structures and combines data, and in the end populates some type of a database. Okay, now many tasks go under information extraction, and I'll be a little more specific on more specific tasks here. So here there's some text, some document talks about Alan Turing, and the task of entity recognition, for example, is that of identifying entities that are specified by their names, all right, and also identifying the types that they have. Okay, so church is a person, Princeton University is an organization, Princeton is an organization, and so on. Another one is relation extraction. Find instantiations of a relation of some predefined specific semantics. Okay, like here, advised by Turing Church, works in Church, Princeton. Temporal information extraction is the part of information extraction that specializes on the temporal aspects, like finding periods of time, what is the start and end of this time, or what is the point time or moment time that is being mentioned in the text. Okay, and event extraction, find the occurrences of some specific events, along with some key parameters of these events, like graduation, who graduated, where was the graduation, and so on. Okay, but who is this he? So that relates to coreference resolution, identifying different mentions in the text of the same entity. Like here in the entity, you have the Turing name and the his and he, which are called pronouns in linguistics that refer to the same entity, Turing. Okay, and Princeton University and Princeton are also the same, so it's not just about pronouns. All right, and so on. Okay, so in terms of the terminology that I'm going to use, so there's always going to be some document, or which I refer to as text or a string, depending on the context, but it's all the same. And then there are these intervals in the text that we refer to as spans. Okay, and we are very specific by the way that we represent them. They're identified by basically the start and end position of this interval. So this is character number 35, and 41 is actually one character after the last. Okay, so now we can also naturally represent the empty spans. Okay, but a span is really just a pair of indexes denoting the beginning and end of the interval. Okay, and what we extract from this document is basically a table over the spans of the document. Okay, we call it a span relation, and this is how it looks like. It has attributes like an ordinary relational database, but the items inside it, or the values, are spans. Okay, so that was just to get us in the context, in the mood of the talk, and this was the introduction. And next, I'm going to talk about several paradigms of how people are actually performing information extraction. And yeah, after that part, I'm going to switch to a more theoretical mode. I'm going to put my theorist hat and talk about this document spanner formalism that basically aims to understand the anatomy of all of these paradigms or programming systems for information extraction. And after I introduce this formalism, I'll get into some specific analysis. This is the part 4 and 5. And then I don't think that I have the time to go into both 6 and 7. And so I think I'll, to the extent of that time will remain, I'll go to the 7th part, which is aspects of systems that are not within like expressiveness and computational complexity. Okay? Questions so far? I haven't said much yet. Okay. So let's talk about some paradigms or programming paradigms for information extraction. So naturally, like many fields in computer science, these things started as rules. People were writing programs that say exactly what to do, how to extract the information, kind of do what humans would do, but in an automated way. Okay? So these are the kinds of rules that you could find in the early systems, but actually people are exploring these kinds of systems even today. So here we have some text, which is a citation of a paper, and these rules are trying to extract, say, the authors and the title and the proceedings of this from this text. Okay, so the first rule says, well, if a word starts with a capital letter, then it is a candidate of an author. This is simplistic, but just to get the message through. And another rule will say something like, if it is all capital letters, then this would be proceedings candidate. And so, okay, we have here, we have here a match of the third rule, which is a title candidate is everything, basically, every sequence of tokens between an author candidate and a proceedings candidate. And we have here one title candidate and another title candidate. So already what we see in these examples is showing kind of the paradigms that people were using in these rules. So first, there is this technique of the Rapier system that basically allows you to state rules like the pre-filler, what should happen, what should come before the text, the filler, what should your text match against, and the post-filler, what should come after that. Okay? And you have systems like gate or the JAPE, to be precise, the JAPE component of gate, which implement basically a hierarchy of such pattern matching rules. Okay, you go, you scan, you match some patterns, and then on top of these patterns, you match the next matcher, and so on. So this is the first type of rules that we can find in such systems, pattern matching. The other kinds of rules are basically relational reasoning. These are rules that operate over the relations that you've extracted in the first phase and do some reasoning that is essentially independent of the text. It's just at the level of the relations that you've extracted. Okay, so here there is a rule saying, well, if you have two candidates of the title and one contains the other, then delete the shorter one. Okay, so we're deleting here the shorter one. And one saying if you have an overlap between a title and an author, then delete the author. Okay, these are say cleaning rules where you're eliminating some of the extractions based on conflicts, and we'll see these kinds of rules later towards the end of this talk. And there's been a lot of work on basically introducing some automation to these systems, like rule learning or rule improvement, taking some rules that have a very high recall but low precision and making them more specific, or the other way around, making rules more general, or dictionary learning. You have these dictionaries that are used within these rules, and people have studied all sorts of ways of building these dictionaries to maximize the precision of these information extractors. Okay, so obviously machine learning came into the picture. And so a lot of the work from the statistical machine learning community views this task basically as a sequence tagging task. You have a sentence or a citation in this case, which is just a sequence of tokens, and there are some labels attached to these tokens, and they can be labels saying these are author tokens, but they can be more specific, like this is the beginning of an author, this is the end of an author, this is in the middle of an author, and so on. And the problem is that these labels are hidden. You don't know them in advance. All you see is the text, and you're trying to guess or make the best guess as of what these labels are. Okay, so this is called, it goes by the name of sequence tagging. So one direct way of using machine learning, the classical machine learning, is by transforming this problem into a classification problem, right? And here we want, suppose that we want to understand, to learn and to guess what is the label of this specific token, right? So we can do what a lot of traditional machine learning is doing: find some, extract some features about this token, okay? And this token is kind of part of a candidate set that you're generating. So you're generating features, and you're trying to classify this, the entity or the token based on the features, and to predict whether or not it is an author. Okay, what could be features? Well, whatever comes to mind, right? Like this is a person name, so it belongs to some specific dictionary, and it ends with a colon, and the first letter is a capital letter. And you can also bring in features from the window. Okay, so you take all of this information and you make a prediction. Okay, is it true or false that this is indeed an author label? And if you have several labels, then you do multi-label classification. Okay, so this is kind of the traditional, or one of the traditional ways of employing machine learning to the task. And then, you know, you can think that the traditional machine learning, or the previous classification approach, kind of makes an assumption of independence between the labels of two of these tokens, and it stands to reason that there is some correlation between the choices of two tokens. If you've made a decision that this is an author token, then it has some implication on the next one being an author, okay, and the title and so on. So one way of encoding these dependencies is via probabilistic graphical models, okay? And this, one of the earlier approaches was this model of an HMM, where the idea is that we assume that there are some states that have labels, and they're hidden, we don't know what they are. But they're part of this generative process where every state, every one of these nodes, based on the state, produces some content. Okay? And what we see is basically the content, the output of this process, and we want to make the best guess as of what would be the most probable sequence of labels to begin with. And this will be our decision of the labels, okay? Or we can ask questions like, what is the probability that this token here is a title? So here we're doing like marginal probability inference, okay? And what these objects, what these hidden states are generating is not just the word, but actually they can generate a collection of features, feature values, okay, like we see here. Then, you know, if you accept this kind of a way of modeling the problem, then people have been asking, like, you know, why do we need to take this way of generating the tokens? We can also look at the other way around. The tokens, or the words of the sentence, are the ones who produce the state of the hidden state, right? The state that we do not see. So this is kind of a generative process of the reverse direction. And if previously, if you think of it previously, the probability, the prior probability over the sentence was determined independently of what you see in the end. What you see in the end kind of defines the conditional probability. And here the probability, the prior probability, is actually depending on what you see on the sentence that you see. And this is referred to as a discriminative model. Okay, so you change the direction of these edges of the generative process, and you get the maximum entropy model. And then you go one step further and say, okay, why do I need to commit to any direction of these edges? Let's just forget about the generative Bayesian probabilistic process, and let's just write an edge between every two states or tokens that we believe that there is some correlation between them. Well, to be more precise, what we write here is basically a specification or a statement that given any node with an unknown, with a probabilistic value, if you tell me the values of all of its neighbors, then I'm basically independent of the rest of the graph. Okay, the value of a node depends only on the values of its neighborhood. That's what this kind of graphical modeling describes. And there is this Hammersley-Clifford theorem saying that, well, if this is the semantics of your graph, and these are the independencies that you have, then you can actually define your problem in the following way. The probability of a specific possible world, of an assignment of values to all of your random variables, is a product of functions of these assignments on the different clicks of this graph that you have here. Okay, so you can always present your graphical model as a product of functions of what's going on in the clicks of the graph. And these are called factors. Okay, factors will generally refer to the product components, the factor of a product that constitutes the probability of a possible world. A very general concept. So now, going back to, what are the features? What are the additional items that are involved here in this graph that are not part of, not just the labels and the text that you see? Well, there are the features. And we can see, this is taken from the book of Sutton and McCollum on CRFs, conditional random fields. And basically, you see here a list of features. You probably cannot see these features, but tell you some of them, like the word, fine, the part of speech of the word, right? So there is some semantic analysis of the sentence up front, and the part of speech of some specific tag is taken as one of the features. Or, like we said previously, does it start with a capital letter? Is it all caps? Does it end with a dot? Is it one of the stop word dictionary? Okay? And we see a lot of these features are essentially regular. They're either dictionary matching or the application of some regular expression. And we will see that this kind of approach repeats again and again, even in the most modern systems. Now, what could a CRF use as features? So we've seen these features, which we can roughly classify into token or word features and edge features. I didn't talk about them, but these are all of the features that are determined by the words or the components that are connected by an edge. Okay? Of course, once you start pushing in the features, we can also include word embeddings that Renee was mentioning today, like Word2Vec of Google, or what was the one you mentioned today that you fastest, right? Whatever word embedding you want, which is basically what is a word embedding at the level of this. My statement, you can view it as just a function that maps every word or every word from a relevant collection into a vector of numbers of some predefined dimension. Okay, it has, of course, to be useful, it has some semantic properties, like words that are close in meaning are also close in the vector space and vice versa. Okay? And if you're starting to introduce these kinds of features, then you can actually push in a whole function, complex function that tries to learn some features from examples, for instance. And for that, you can use, say, what is commonly used today, the deep neural network. So here's one way that seems to be quite successful, highly cited, of introducing the deep neural networks into our into the framework, basically into the graphical models. So if you ignore the orange circles, then what you have here is a CRF. You have these hidden states connected to the words. Now these circles, they just add some new features. And what are these features? Well, they form some complex function. Okay, this is, by the way, a work of Wang, Chu, and Yu, and this is just their explaining their framework. So what you put here is just a complex function, right? And in the world of deep neural networks, they like to present it in this way, but this is just says that what you have here is a complex function that gets the word or the embedding of the word as input and does some stuff and computes a function, ht, which again is some combination of the values of x, but also the value of the previous invocation of this cell. This LSTM, so this is why it's called LSTM, a long short distance memory. So this is the memory. The output of the previous cell goes into the next cell. So this output goes as features to the LSTM plus memory between these cells. Okay, and this is how you extend the CRF concept fairly simply with this idea of LSTMs. Okay, so again, just we were looking at it as a more complex feature function, but it is more complex, but it has a predefined structure, the structure of this LSTM, and richer memory. We're not just passing information from one hidden state to the next, but also between these cells. And it has obviously more parameters that require more training data to tune. All right? Okay. So now, going back to 2012. So there was this study showing that although there was a lot of progress in the statistical models for information extraction, when you're looking at, or when you were looking at what people have been doing in the industry, a lot of it was based on rule systems, deterministic systems. Here, so what is this chart showing? So the dark area are solutions that are purely machine learning based or statistics based. The light gray area is like ideas or systems that are purely rule based, okay, paradigms that are purely rule based, and in between you have the hybrid, which include all of these ideas of incorporating the rules with some automation, okay, hybrid systems. And what you see here is that in the academic world, most of the solutions, most of the papers were on the statistical model or machine learning models, but in the industry, especially in the large vendors, most of them were either rule-based or hybrid. And the reason is that these statistical models, they can get you far in a short amount of time. You deploy some known statistical model, you train it, you give it some examples, and it gives you some impressive numbers in a short, in a short amount of time with little effort. Problem is that it's difficult to tune it. It's difficult to understand, to explain why it makes some specific decisions. It is difficult to nicely incorporate some domain expert knowledge. Like if I know of some cases where this is the extraction that should happen, or this is the intermediate result that should happen, it's difficult to incorporate it without messing things around. And okay, so the advantage back then of these rule-based systems were that they were allowing you for this full control as which was important for businesses, for industry. Okay, and there was some support in the academic world by Gupta and Manning. Manning is probably the most important NLP scientist, who said that the rules are effective, interpretable, easy to customize by non-experts to cope with errors. So at IBM, they were developing this System T system, which you can think of as basically SQL for text. SQL was very successful, right, by everyone, and then very well used, easy to use, right, empirically, people of all sorts of skills are using it. And the idea was to replicate in the example. Okay, so what is the difference still from SQL? So you see that in SQL you would do something like create, view this and that from some relation of a specific name. So here there are no relations. Instead of calling some relations by their fixed names that you have in the schema, you're going to the text and you're extracting some information. How do you extract this information? So here we see some regular expression applied to the document. And here we see some dictionary matching. Okay, these are what we'll later refer to as regex formulas. They go into the text and extract some attributes or some more complex relations. Okay, and then you can also call these relations that you've extracted and do some joins, but say more of a text-related joins, like the distance between the spans and so on. You can also incorporate with these base relations some libraries of natural language processing, which is basically my engineering task at IBM was to incorporate NLP libraries into System T. But you can also read about it in this year's KDD tutorial on System T. They go deeper into how they incorporate semantic parsers and so on. Okay, and then you see other relational operators like projection, union, just the usual relational operators. And then you see here some cleaning phase that I mentioned earlier that says, well, if you extracted two names and one is longer than the other, one is contained in the other, throw away the shorter one. Like if you have people's names with consisting of 3 tokens, like first name, middle name, last name, and you extracted like first name, last name as, or first name, middle name as the full name, throw it away. Okay, so again, these are cleaning rules that I'll mention later. So now, in time, there evolved some concepts that basically allow us to think of it as enjoying the best of both worlds. The world of logic and rules, and the world of weights, statistics, softness, and so on. And there are several ideas of that, but all are basically based on the assumption of you extract information using rules, but you treat these rules in kind of as a recommendations. They can be violated. They can even contradict each other. That's fine. But you just need to be very specific on what is the semantics of what you do when some of the rules fires and some do not. Okay? But basically, think of it as they're describing or specifying a probability space where the probability of a possible world is somehow determined by the extent to which the rules are being satisfied or violated by this possible world. This is the commonality of these paradigms, the soft logic paradigms. And then once you have this probability space, you can do whatever you do with the probability spaces. Inference. What is inference? Most probable world, probability of an event, conditional probability, conditional most probable world, and so on. All right? And some some of the concepts that go into this category are starting with the Iago's very simple idea of just maximum satisfiability. Find the set of facts that would satisfy the most, the maximal number of rules or rule instantiations with weights. And there is this concept of Markov logic networks that I'm going to mention later. Probabilistic soft logic, PSL, of the Liske-Tur work that René is familiar with. It basically moves from a standard logic to multi-valued logic. So a fact is not necessarily just true or false, but it has some degree of truthfulness. And again, it allows you to define a probability space. And this continuity is the key in getting some significant performance gains, right? It's faster than other solutions. And more general specifications of factor graphs, I'll mention that also, right? So here's an example, again, a simplistic example of Markov logic, okay, of how Markov logic works. So here we have, well, in the context of text, Markov logic is more general, right? But I'll explain it in the context of information extraction. So we have this document, and we have, in the possible world, basically a schema that consists of two relations. First relation says the text at some position is whatever the text is, and the tag at some position is whatever the tag is. Okay, so for example, in this possible world, the text at token 10 is theorem, and the tag at token 10 is t. All right. Now you have these rules. A rule saying, well, if the token at I minus 1 is a, then at I it should also be a, right? The following token should also be a. Well, obviously you don't want this rule to fire or to be true all the time, but it has some information about the correlation between the tags. And if the token or the text at the token I is something that occurs in your person name dictionary, then the tag should be author, right? This is a rule of positive correlation, probably with reality, and several other rules, like this one saying title should always come before author. Okay, it's violated in this rule, but probably in other citations it's correct. So now, given a specific possible world, we're looking at these rules, and they have violations. For example, if the tag at I minus 1 is a, then at I is also a. So if you look here at I equals 8, then you have a violation, because at 7 it's an author name, and at 8 it is not. So you get a violation, and you're kind of writing down the weight of this violation. You have another violation of the second rule. You're writing down the weight, 5, 3. Here you have several violations of these title comes before a author thing, like right, 5 and 9 are an example or grounding of this violation. So now, this is the idea. The probability of a world is simply product of the weights of the violations, right? It is the exponent over the sum or minus sum of all of these violations. You just push in all of the weights of the violations, and that determines the probability of your world. Right now, a key property of this approach is that these costs are not things that you should mention yourself. They can be learned from examples. Okay, that makes things much easier to use in practice. And also there are other macros and convenience components, for example, that you do not need to mention this rule for every author, and it's basically a separate rule with a separate weight for every tag. If you think of what we've been doing here, then we have basically been building what is called a factor graph. A factor graph has always this structure. On the one side of this graph, you have the random variables, of which values we don't know a priori, right, up front. And on the other side, you have the factors. These are functions. This is a function that gets as input the values of these random variables, or the random variables that it has on the other side, and gives you a number, a value. And the probability is always a product of these factors, normalized by the obvious normalization factor. Okay? So with Markov logic networks, we've been basically building this random graph, but in a very compact way. Instead of saying, well, this fact here, this extraction is true or false, we've been saying, well, for every instantiation of this rule, these are the facts that are involved in this instantiation, and this is the factor that looks and see if this the rule with these specific facts is violated, then the factor is the cost of the rule. If it is not violated, then it is 1, something that has no impact. Okay? But this is just a concise way of building a factor graph over the random variables, which are, is the tag A or is the tag T, and so on. And then you've seen systems like Deep Dive that took this approach a step or several steps further, and basically allow you to encode more general classes of these factor graphs. These factor graphs can include the numbers, you have more control over them, and this system is basically an end-to-end full text analytics workflow. So that's also part of the differences from Markov logic. And has a nice support for many text operations and external Python functions and so on. Okay, and another important feature of this system is that it allows you for what is called distance supervision. Distance supervision means that you can produce labeled data, but noisy labeled data. It's like positively correlated with the golden truth, but it may have errors, and it may have a considerable number of errors. But the learning methodology kind of allows these errors to occur and adapts them to the level of error. So this is the idea of the distance supervision. And in this next step system, the Snorkel system, this has been taken several steps forward. And in this system, basically the idea is forget about the features, forget about feature engineering. We're not doing that. We're just programming labeling functions, distance supervision. All the user needs to do is write these labeling functions, and I'll give some examples of these labeling functions next, that produce many examples of extraction. And these extractions, may have, well, you can tag them as positive examples, negative examples, and all you require is that there is some reason behind them. They have some positive correlation with reality, but we can make a lot of mistakes. And when you have many of these, you're trying to build some model without knowing the actual truth, making some, building some model of what could be the real value, the real label of the tag, again, assuming that these labeling functions make sense. Okay, and in their publications, they also build some theory to explain why such a workflow makes sense and why they actually converge to the real values. And what does it give you? Well, if you have all of these labeling functions, that allows you to produce many, many more labeled data than you would do manually. With this amount of labeled data, but noisy labeled data with some probabilities. With all of this labeled data, you can now train a complex system like LSTM that goes into the text and tries to learn the function or the information extraction to begin with. Well, what it should have been to begin with, regardless of all of these labeling functions, right? So this is basically a way to train highly complex networks without the usual cost of producing many, many training examples. Here are examples of these. Yes?
Sorry to interrupt. I mean, I was just reading, so when you first introduced the first example that you gave, there the rules themselves were still, let's say, manually written, right? You said, okay, the probabilities can be learned. Because it's correct that actually what you're saying in Snorkel is that actually there the rules are also being manually.
Well, what I'm saying is that there are no rules. Well, if you look at these features, they kind of, these rules, they play the role of the features in machine learning because each of them contributes a factor. You're basically saying, I have this many, this factor 3, and you have it as many times as you have this rule being invocated. And basically, and this is the same idea in Deep Dive, just more general. But in the Snorkel system, they basically said there are no features, there are no factors, there are no rules, there are only examples. The rules that used to be defining the features are now, or the factors, are now defining the labeled examples. And there is more automation in the background, in the system, to basically accommodate the fact that there are no rules and no features, just examples. Okay, but there are the rules are somewhere in the system, and the manually written rules are somewhere. Just move from this part to that part, right? To this training data part. Yeah. Okay, so we're looking at some rules from the Snorkel tutorial online, and here are the links. So this rule says, well, think of here, I hope many of you or all of you can see the text. But here, think of X, or X here is the span that starts with a person mentioning and ends with a person mentioning. And what you're trying to do is to extract pairs of married people, okay? So this is again, from the Snorkel tutorial. So the rule here says, if between the first mention and the last mention, the two persons, there's the word married, just the word exists married, then mark it as a positive example, okay? And of course, it may have its mistakes. The second rule says, well, if they have the same last name, string equality on the last name, then they are married. And the third rule says, if there is any word between that indicates a different type of a relationship, like professional or boyfriend and so on, then it's a negative example.
And anything else
All right?
is married?
No. It means that if you see this evidence, this witness, it is an indication of a negative example. So you will produce a noisy training instance of this is not, this is an indication of a not married relationship. You can also at the same time have another reason to believe that this is a yes married relationship. This is the part of the noise part of the labeling function. But here you just need to say, well, I produce a labeled instance, and I also tell you what is the label of this instance. This is positive, this is negative. Okay? So this is probably, took me way more time than I expected, but this is probably the most important slide in this part that I want you to remember, which is that the rules are incorporated in these systems. We are not looking at the world of there are rule approaches and rule systems versus statistical systems and machine learning. The rules have never been abandoned. They just change their roles. So they can be used as full deterministic programs like System T, but they can also be used as features of the classifiers that we talked about, or these are features of the graphical models and the CRFs. They can also be used as the factors of a factor graph specification in soft logic. And they can also be the generators of labeled data, noisy labeled data. Okay, the rules are all over. It's just that they have different roles in these statistical models. And what you see here is really some synergy between the rule system and the statistical model. This is what you see in this world of information extraction. It just work together. If you think of a rule system as providing the features for and the labeled data for the statistical model, you can also use the rule systems in order to clean whatever the machine learning has done and violate some common sense logic. You can also take it the other way around and use some statistical models and machine learning models in order to clean whatever you extracted using rules. And of course, you can use whatever statistical models are producing as the building blocks of logic. Okay, and use it as your relations on which you apply, say, SQL. Yes?
So in distance learning, how do I know that my rules are positively correlated with what I want to learn? You gave an example where you said if two people have the same last name, then they're married. And I imagine on some corpuses, if the corpus is all about the Johnsons, that rule is not positively correlated with being married.
Well, good point. I'm not at all an expert of the of what's going on inside the theory of Snorkel, but this is an assumption, and if you want to verify this assumption, I guess you need to do some manual work, right? But yes, in that extreme situation, you have a problem. But think of it like, if all you do in the system, look at this, what the user is doing in the Snorkel system. It loads in the data. It chooses some generative model, which can be a generic model. And up to this point, with these two items, the problem is not different. One problem instantiation is not different from a different problem or another different instantiation. If you want to find married people, you provide it with the same input as finding employees or manager employee or unmarried people. This is the same input. So what is the difference? Well, there should be some difference in the input, otherwise you're defining the same output, right? So the difference in the input is really in these labeling functions, and you need this labeling function to make some sense. The theory behind Snorkel says that this sense can be quite limited, but there should be some epsilon. The probability should be 0.5 plus epsilon, not 0.5 or 0.39. All right. So this is my limited understanding of what's going on there. Okay. So basically, I've been talking about these programming paradigms for information extraction, and specifically the role of these of the rules inside them. I'm going to, as I said, I'm going to now switch mode to a more theoretical, more low-level mode with much more attention to the details, not the hand-waving that I've been using so far. And this is based on formalism that we developed. I started developing when I was back at IBM, and this was a collaboration with Stein, Van Summeren. So, yeah, Stein, stay where you are because I'll point to you frequently in the next parts. All right. So this is a very basic definition, the document spanner. It just basically is a concept that encodes what we've already seen. It is a function that takes a document, or a string in this case, and maps it into a relation over the spans. This is the definition. A document spanner is a function that maps every string into a relation over the spans. Okay? There are several things that we need to still know about the theoretical specs. Some details like we assume a finite alphabet, sigma of the symbols. And then a document is basically a string over these symbols. And as I said previously, the span is written as the ij, the beginning and the indices. And also the spanner has a predefined schema. It has a set of attributes. And every document is mapped to a relation over this predefined set of attributes, like married, okay, or person name, or married person 1, person 2. Okay, so the definition is abstract. It is not at the level of what it extracts, or just one second, how it is represented, or even how it is executed with a specific representation. You can use it as a generalization of, say, generic natural language processing libraries. And it's very easy to instantiate them with existing libraries like, to name a few, NLTK, Core NLP, OpenNLP, LNNLP, very successful libraries that have been developed, some lately, some older. They can also be programmable constructs like regular expressions or dictionaries, dictionary matchers, automata, deep networks, and or SQL. We'll see examples of that. Yes, please. Yeah.
I was wondering, so you basically translate everything to relations, right? In this document, into these like triplets.
Yeah.
So I was wondering why that is. So theoretically, you could also think about other data structures. So
Right, absolutely, and we did think of we and others have also thought of other data structures, but this is the data structure of choice. The motivation really came from System T, where this is what they've been doing, building relations and applying SQL to them, and trying to understand what is this marriage between a relational query language and text analysis is doing. But of course, you can think of other models. The relational model is very general, right? And it is able to encode, in many cases elegantly, many other data models. But of course, JSON and the incompleteness models and so on are of interest. And in fact, people have been looking at them. So I'll mention a few of these extensions later. All right. So here is this concept of Regex formula, just a way of representing spanners using regular expressions, right? So a regex formula is basically a regular expression with capture variables. The definition is the usual one about a regular expression. It can be the empty set or the empty string or the symbol that consists of this specific alphabet symbol sigma, or it can be exclusive or either gamma of one form or gamma of another form. It can be the concatenation, the Kleene star. This is the usual regular expression. And we also allow you to use this construct, which is a variable x, and inside it you put the regular expression that you match into this x. Okay, so for example, if you have some regex formula like this, like star or dot star x, inside x you have 4 digits, okay? And then dot star, it extracts all of the cases of, or matchings of 4 digits in the document. Or something like star in, and then matching of some dictionary, like the state dictionary. Then W will capture the span of this dictionary. And you can have some variables inside one another, okay? Now we do have here a strong assumption. Basically all of the work on spanners is making this assumption that the regex formulas are so-called functional in the sense that every parse against a string gives you precisely one assignment to every variable. So I won't get into the formal definition, but it means, for example, that if you have some expression of that, gamma 1 or gamma 2, then the two gammas should have the exact same variables. Or if you have a gamma dot, a gamma concatenation, then the sets of variables should be disjoint. Or if you have a star, then you're not allowed to use any variables there, because then you can have multiple occurrences of the same variable. Okay, so this is an assumption that we're making. So now, if we have so this is a representation of a spanner, all right? And if you want to analyze regular expressions, of course, the automata is a convenient tool for that. So just to remind you, the concept of a non-deterministic automaton means that it's this structure here, this machine here, that goes through the text and makes these transitions between the states. It can make some epsilon transitions, like it reads nothing, just makes a transition. And in the end, the question is, am I or am I not in an accepting state? Okay, and then this is a classifier. It classifies the strings into yes and no. A spanner automaton is doing the same, but it allows you to open variables and close variables in some of these epsilon transitions. Okay? So in the end of the run, which should be an accepting run and in an accepting state, if you look at where x has opened and closed and where y has opened and closed, then you get basically an assignment to x and y, to the spans of x and y. Okay, so every run gives you an assignment to the variables, and again we're making this functionality assumption that indeed every accepting run well behaves with the variables. It opens every variable once, and after it opens it, it closes it. Okay, and it is a non-deterministic automaton, which means that it can have multiple runs, which means that it can have multiple assignments to the variables, and therefore this is again a representation of a spanner. Right? Any questions about?
Yes.
Yeah.
Is there some sort of like criteria to determine? Because this, for example, can be ambiguous. I mean, like where y, for example, starts and where it ends. If we do a lot of loops, then have a lot of possibilities to interpret.
Right. So it's important. The ambiguity is very important for us. It's important for us that this automaton can extract different tuples. So one accepting ground gives you one tuple. Another accepting ground gives you another tuple. That's the way for us to encode a spanner that maps a document not to a list of assignments to the variables, but actually to a table of assignments. Every entry in this table is one run. Okay, and some of them can be the same. All right? Yeah.
There are no restrictions whether two different runs give you the same assignment?
This is fine. It can happen, but when you do complexity analysis, this is a source of headache. But for the definition and the expressiveness analysis, this is fine. But yes, Stan is smiling there. All right. Another one that I need to define because we'll be building these languages or these formalisms composing different spanners on top of each other is this equal string spanner. And it basically adds to the regular expressions this important capability that automata do not have, regular languages do not have, which is identifying the two spans correspond to the same string. They span the same string. Okay? So remember that this is the spanner that I call equal string. It gets these parameters x and y, and it maps the variables x and y to all the spans, pairs of spans in the document that have the same string. Okay, like here these two spans, there are different spans, different places in the string, but have the same string. Okay, and if you think of it, it's actually an equivalence relation over the spans. It is a reflexive, symmetric, and transitive. Okay, so we have here these two spans, but also this span in itself, and so on. Okay, so this is another representation of a spanner, and so far we've been looking at three classes of spanners: the Regex formulas, the spanner automata, and the equal string. Now, when you have a spanner, you can apply it to a document, and you're getting a table. You can apply a different span to the document, you get a table. But now you have two tables. You can apply a relational query language to these tables, whatever that is, relational algebra, SQL, and so on. And then you get a new spanner. Okay, a new table and a new spanner specification, right? It is the composition of spanner 1 and spanner 2 through the relational query language of choice. Okay, so we can think of, say, the relational algebra. And here we're looking specifically at the natural join, union, projection, rename. These four we refer to as the positive relational algebra. Okay, here note that the natural join means that we are comparing spans against each other. Two spans are the same if they are the same spans, not the same string. They are in particular the same string, but they can be same string, different spans, and they will not join with one another. That's why we need this equal string spanner. Okay, and then when we add the difference, we call it the relational algebra. And we observe the absence of the selection operator. And the reason is that because we are joining with relations that we can construct, for example, using regular expressions, we can do these selections by joining with the conditions that we want. Okay, so instead of selection, we do natural join with our condition. This is just a cleaner way of defining what exactly do we have in this language, because if we use the selection, then we would also need to explain or specify what are the different conditions that we allow you to encode in this natural join, in this selection. Okay, so no selection. Okay, so here is an example of a query.
Sorry, that means that you have only positive selection.
Well, what do you mean by positive selection?
Selection with the equality condition.
No, so for example, the selection that says the two spans start with different letters, for example. So you would construct the spanner that extracts all pairs of spans that start with different letters, and you would do the natural join. Okay, so because we can encode, these are not given relations, but these are relations that we encode, we can incorporate the condition there, and then apply the natural join. So this gives us the selection. It's just a way. Actually, in the papers we do mention selection, but here it's just simpler and of equivalently with the same expressiveness, presenting it in this way. All right, but in the relational model it wouldn't work, because in the relational model you can only do the natural join with given relations. So you cannot say, okay, I'll encode my condition as a given relation. No, the relation is given. But here we can actually construct this relation. Okay, this is one of the differences. Okay, so this is an example. And we're basically looking for all the x1 and x2. This is the projection, such that we get the x1 and y1 from the name SSN. Let me go to the next slide to make it clearer. So x1 and y1 occur in the name SSN relation that is extracted somehow with a spanner, and another join with name SSN. So this is x2 and y2. And y1 and y2 are actually equal to each other. And then x1, she's like this one, and x2, which in this example is this part, John Doe, belong to the same paragraph. What does it mean? That x1 is in a paragraph C, and x2 is in a paragraph Z, and this is the same C, right? So think of it, conceptually, what we're doing is that we're building all of these relations and just applying the relational algebra to these relations in the usual way. Okay, and we're getting the answer. Questions? Okay, and so I'll just finish this part. I'm very close to the end. So instead of the relational algebra, you can use, say, data log, which just looks like that. Here in this program, we extract all the tokens, and then all the state tokens, which are the tokens in some dictionary, and then all of the tokens that start with a capital letter, and then two tokens that are separated by a comma. All of them get into this Z span, and then Z is a location if it is a first couple word followed by state, a word state span, and they're all part of this X, Y, Z comma separated relation. X is separated from Y by a comma, and they both get into Z. Okay, so then Z is a location, and then we're looking for patterns like X from Z. Okay, if you have this document, Carter from Plains, Georgia, then it gives you Carter and Plains, Georgia, and okay, and it's important that we have this return statement here because this defines the output of the spanner. Okay, so if we have now these languages for primitive spanners that we defined previously, we can also now combine them with several languages for the relational part, several relational query languages, and now we can start combining between them, right? If you take the combination of the relational algebra on top of the Regex formulas, then this gives you what are known as the regular spanners, which are most widely studied so far. And if you take the positive relational algebra on top of the regex formulas and string equality, it gives you what is called the core spanners, which is considered the core language of the system T, and has been studied in different variants and different logics, like the Splog logic of Friedenberger. And if you're taking, say, the whole relational algebra, including difference, on top of these two, then you get what is known as the generalized core spanners. And if you take data log on top of regex formulas, then you get several languages or several names of the same language. The Wisconsin group has called it Xlog, and in the most recent paper we called it regex log. Okay, so just data log over regex formulas, the example that I've shown, and that's it. So basically, here are some pointers to where it is implemented, and I think the prime resource or prime implementation is IBM's System T, and this slide I'll give in the next part of this lecture, but I'll end with this slide that lists the names of the people that I collaborated with over this topic over the years, and it's my opportunity to thank them. So I'll just leave this slide, and I think we're good on time, right? I'm 1 minute late. All right, let us continue. So, right. All right. So I'll start with this last slide that I promised to give after the break. So I've defined this concept of the spanner and kind of the main formalism that have been studied. Now, what research was done over these spanners? So to date, most of the research was basically using the spanner framework to understand the fundamentals of the query languages or languages for specifying information extraction. Specifically, there's been a lot of focus on this interplay between text operations and the relational or structured operations. Questions like, does the relational capability extend the expressive power of models? Okay, and we'll see that the answer is sometimes positive, sometimes negative. And questions like, does the holistic view, viewing the programs that involve both the structured part and the unstructured part, is it something that can lead to better algorithms, to lower complexity, like fundamentally lower complexity, rather than just applying the text operations, pushing them to a database engine and letting the database engine do the structured analysis? And we'll see that the answer is positive. Sometimes this holistic view leads to reduces the running time from exponential to polynomial. A lot of research on applying concepts in databases to information extraction and adapting these concepts that were used nicely in the database world. And we'll touch upon some of them, depending on the time that I have left. And some topics that I won't mention that basically relate this framework to CSV querying or CSV generation and ontologies. Okay, so in the next 2 parts, I'm going to talk about the analysis of expressiveness and the computational complexity. Just just to understand the audience, like, raise your hand if your main topic of work or topic of research is more on the theoretical side than the practical system implementation side. Like, I'm. All right, we are a few of us. All right. So feel free to stop me and ask and interrupt. Okay, as usual. I mean, I won't go through all of the content anyway, so I might as well do something that people maybe understand. All right. So expressiveness. So, let's start with a simple question or the simple exercise. We have the regex formulas. Remember, these are the regular expressions with capture variables. And we have the relational algebra on top of the regular expressions. Okay? These are the regular spanners. What is the relationship between their expressive power? Of course, regex formulas are contained in the more expressive or the richer language, but what about the other direction? Like, what is the extra expressiveness that the relational algebra adds to the regex formulas? Well, this is an easy question because the regex formulas have this property of being hierarchical. Whenever you extract something from text, the spans have this relationship of for every two variables, their spans are either disjoint or one contains the other in every tuple. In different tuples, across different tuples that can be different, but on every specific tuple, you have this property. And regex formulas can only create these kinds of hierarchical extractions. And something that is non-hierarchical is that, like, these two spans that have an overlap between them, but no containment. So, yeah. So it's easy to see with that with the relational algebra, we can get things that are not hierarchical. Like, take the Cartesian products of all the spans with all the spans. That's not hierarchical. Okay. The interesting thing here is that the regular expressions, in terms of expressiveness, capture precisely the regular spanners that are hierarchical. If you take the regex formulas and close them under the relational algebra, then what is the portion of that the regex formulas have captured to begin with? Well, these are precisely all of the spanners that are hierarchical in the end of the process. Okay, if it's hierarchical, then in terms of expressive power, you didn't need the relational algebra. Okay, so this is the first statement, and we get this obvious containment. And now one of the most fundamental theories in this framework is the following: that the spanner is regular, that is expressible as relational algebra on top of regex formulas, if and only if it is representable by a spanner automaton. Okay, so you take this formalism, relational algebra on top of regex formulas, and you take this formalism, the regex formulas, they have exactly the same expressive power. And so this class of regex, the regular spanners, you can also describe it as the class of spanner automata, same expressiveness, or relational algebra on top of spanner automata, because we know that this class is close to the relational algebra. So this doesn't take you outside of the spanner automata. This has the same expressive power. Yeah, it can also be shown that you do not need difference. which is somewhat surprisingly, but the positive algebra on top of the Regex formulas has the same expressive power as all of the algebra, including difference, on top of the regular spanners. And the reason is that you have a lot of the expressive power in the regular expressions themselves, all right? So you can trade between the expressiveness of the relational algebra to the expressiveness of these atomic extractors, the Regex formulas. Okay, so all of these have the same expressive power, and this is the class of regular spanners. So yeah, one immediate consequence of this theorem that Regex, the regular spanners are captured by the spanner automata is that you cannot do string equality with a regular spanner. This is obvious to everyone who works with the spanner. Just it connects to the very basic properties of automata and regular languages. So then we can continue this picture here and establish that the regular spanners, which we can view as positive relational algebra on top of Regex formulas, is strictly contained in expressive power in what you can do with positive relational algebra on top of the Regex formulas and string equality, the ones called core spanners. Okay? And I'm going to continue with this flow. Any questions so far about that? All right. So the question is, do we need the strength of the relational algebra? Do we need difference to increase the expressive power? Or put differently, is this class, the core spanners, is it close to difference, okay, to the non-positive algebra? Okay, now this is an interesting story. It took us quite a while to get to the answer. One indication that the answer is negative is that there is no reason to believe that it is closed under the relational algebra because we're using under difference because we're using only the positive relational algebra. But again, we've seen an example where you're using only the positive relational algebra and you're getting the expressive power of all the relational algebra with difference. It is because regular expressions have the expressive power of their own. Okay? Then we thought, let's try to prove that something is inexpressible by these core spanners. So what did we add to these core spanners? We added string equality. Let's pick a candidate and try to prove that it is inexpressible in the language. Like, say, string inequality, right? This is what you would get from difference. And we had several proofs of why you cannot do string inequality, but each of the proofs had a bug in it until we realized that you can actually do string inequality with these core spanners. And the reason is very simple. If I'm asking you to write a program that determines, in this formalism of the core spanners, that determines whether two strings are not the same, then you can say it equivalently as the strings are the same up to some point. And then at that point, there is a character that is different between the two. Okay? And there are other cases, like one is contained in the other and so on. But basically, what I've just said, that there are two strings are the same up to some point and so on, this is easily expressible, or this is easily codable in the language of core spanners. Okay, so now we're confused. Is it or is it not close to difference? And then the answer came from this relation, the substring relation. Okay, if we're adding a string equality between spans, and we're asking, can you do substring equality? Like one span, the string of one span is contained in the string of the other span, and it is easily expressible as a core spanner. But the thing is that the non-substring relation, the complement of that, is not expressible in the language of core spanners. And I'll say a few things about the proofs, but we conclude from that, in particular, that the class of core spanners is not closed under difference. Okay, so a part of the challenge that I've written is to play with these substring and non-substring relations and code them in the language of a data log on top of regex formulas. And we'll see that the recursive nature of data log allows us to write this non-substring relation, which is, again, not expressible with regex formulas and our relational algebra and string equality. Okay. So we conclude that the core spanners are not closed under difference, and so this class is strictly contained in this class, which is the same, just with difference. Now, to prove this theorem, we needed this central lemma that we call the core simplification, which says that whenever we have a spanner in this language, the core spanner, you can always define it in the following structure. You can normalize it or transform it into this form that is fairly easy to reason about. And this form is as follows. You have a regular spanner, like a spanner automaton. You join it with a sequence of string equalities, and then you apply the projection. It's enough for you to reason about, in terms of expressiveness, it's enough to reason about expressions of this sort. And over expressions of this sort, we were able to show, for example, that there are certain relations, like non-substring, that you cannot do with the core spanners. And I'll refer to this lemma later. I'll explain why it is an important part of the story. Okay? But you can show that you cannot do, as expected, the same length of the strings or recognize like 0n, 1n in this technique. All right. So now we're bringing in the last language that I'll discuss, which is regex log. Data log over regex formulas. Okay, and we've seen an example of that. So on the face of it, it doesn't seem like there is any obvious connection between regex log and core spanners or generalized core spanners for two reasons. First, this class allows me to use string equality, and here I do not allow it to use string equality. In addition, this is in this class we allow negation or difference. In data log, we're looking just at positive data log. But on the other hand, data log has recursion, and many of us know that what you can do with the recursion is pretty far-reaching, right? So it's not clear that there is any connection between the two. But in fact, we can see that recursion allows you to do things like string equality. Okay, the spans of x and y are spanning the same string. If they're either both of them span the empty string, or there are x prime and y prime such that x is the concatenation of x prime with a, and y is the concatenation of y prime with a, same symbol, and x prime has the same string as y prime. Okay, and you do that for every symbol, and that's it. That's your program for string equality. So you conclude immediately that in this subset of the zoo, the core spanners, which are positive array over these guys, is a subset of regex log, data log over regex formulas. Okay, now, what about the generalized core spanners? Again, how do we deal with negation? So here we faced a problem that, which took us quite a lot of time to resolve. All of the inexpressiveness proofs that we've had on the core spanners were relying on this very specific lemma of the core simplification. Again, that you can have this very simple form and you can reason about finiteness and so on. This is something that breaks if you have negation. It is, well, we don't have a proof that it exists, and there are some theoretical indications on why it's not likely to exist by Friedenberger and Holdek. So we're kind of stuck showing any reasonable, showing any bound or lower bound on these generalized core spanners. And the solution came from this topic, old topic called Presbyter Arithmetic. And I'll try to explain it, and it's actually quite, the connection is quite simple. So, what is Presbyter Arithmetic? This is basically first order logic over the natural numbers, okay, 0, 1, 2, and plus, okay, under the usual interpretation. 2 plus 7 equals 9, all right? And so in terms of logic, you have the constant 0, 1, and plus, and your domain includes the natural numbers. And you can say things like, well, n, the number n is even, by saying, well, there exists x such that n is equal to x plus x. Or n is not divisible by 3. You can say, well, for all x, it is not the case that n is equal to x plus x plus x. Fine. And remember that there are some properties that are known not to be expressible in this Presbyter Arithmetic, PA, like n is a power of 2. There is no PA formula that is true precisely when its input is a power of 2. Okay, this has been known for a long time. How is it related to what we were doing? Well, think of the case of a unary alphabet. You have only one symbol in the language. Not a very interesting case, but it's something that gives us some way of reasoning about the expressiveness. If you have only one symbol in your alphabet, then all of the strings are basically the same, except that they have different lengths, right? So a string is really an encoding of a number. And a spanner or a Boolean spanner, or a Boolean core spanner, or generalized core spanner, is just a logic about numbers, about the length of the documents that they have. And so you can look at the Boolean spanner and say, it accepts documents of length this and that, and rejects or doesn't accept documents of the rest of the lengths. So if we take this viewpoint, the Presbyter Arithmetic and the Boolean spanners kind of speak the same language, formula over natural numbers. All right? What we've shown is that basically the class of generalized core spanners has the exact same expressiveness as the Presbyter arithmetics. Again, when you view it as a logic on top of numbers. Okay? To be more precise, the following statement is the following statements are equivalent for a set D, like capital D, of documents. First statement: there exists a Boolean generalized core spanner that is true precisely on every document in D. And second statement: there is a formula in Presbyter arithmetics that is true precisely when the length of the document is satisfying what the formula is stating. All right? And as a corollary, we conclude many things, but for example, there's no Boolean generalized core spanner that can recognize documents of which length is a power of 2. Okay, if this is the task, then it is impossible. Yes?
In this group, you are not using the spanner part of the spanner. You're not using the mappings that are over here.
What do you mean?
The mapping that the spanner gives us output. It just says just
Oh, okay. Well, we use the output and of the spanner. But think of it this way. You have these spanners, they produce output. And then you compare between these outputs. But in the end, you project everything out. This is the Boolean part. Well, good point. It's not like every spanner is Boolean along the way. But the final result is Boolean. You take the projection over the empty set. And all you care about is whether there's at least one match or nothing. This is another way of saying that. Instead of Boolean, say the property of there's at least one answer or there are no answers at all. But we definitely use the variables. They have an important role. Yeah. All right. So and this relationship to Presbyter Arithmetic is something that was already established before our work, but not on the generalized core spanners, but just on the core spanners. Okay, so here is one thing that I can do with regex log, data log over regex formulas that I cannot do, as we now understand, in the generalized core spanners. I can do power of 2. Okay, so a string is of a length that is a power of 2 if it is of length 1, or it is the concatenation of two strings, each of which is of length that is a power of 2, and they are equal to one another, or they have the same length. This could also be easily done in regex log, but we've seen how you do string equality with regex log. So this is basically the proof that with, or one proof that with recursion, you can do things that you cannot do with the generalized core spanners. Okay, so this gives us this direction, like the regex log, the data log of regex formulas, is not contained in the core spanners. What we do not know is, well, at this point, what we do not know is what happens in the other direction, and I'll answer it in the next slides. So let's talk. Any questions about that at this point? Okay, so let's look at regex log. What could be any upper bound that we could place on regex log? Well, think of it this way. We have a regex log program. This is a fixed program, and now the input to this program is a document. And you're starting to apply the rules. All our positive rules, extracting regular expressions from the, extracting spans from the document using regular expressions and reasoning about them in a recursive manner. Well, if you just apply the program and produce these tuples again and again using the rules until you get to a fixed point where you cannot add any more tuples to the program, then this gives you, well, an evaluation algorithm. This algorithm is actually a polynomial time, because remember that we fixed the program. The tuples that you produce are of some fixed dimension, and the domain is always just, quadratic in the size of the document, what you can do by selecting two indices. Okay, so if you just apply the program in a naive way, you get a polynomial time algorithm. Okay, so that gives us it is a complexity bound, but it gives us an expressiveness bound. You can only do with regex log what you can compute in polynomial time. Okay? The interesting thing is that this gives you precisely the expressiveness of Regex log. Regex log can extract precisely the spanners that are computable in polynomial time. Okay? And it's basically because with the recursion, you can kind of simulate a Turing machine and count its steps by simulating this polynomial. Okay? So there are many consequences of that. For example, Regex log, although it is only positive, it is actually closed under difference, under negation. And and other consequences. So in the end, what we get is that the generalized core spanners on unary alphabets are of the same expressiveness as the Presbyter arithmetics, and it is a strict subset of Regex log, which is equal to the class of polynomial time spanners. Okay. All right. Any questions? This is the last slide of this part on the expressiveness. All right. Good. So now we'll talk about. Did you have a question? No. Now we'll talk about complexity, the complexity of spanners. Now, before we go on to the complexity, I want to clear away a few points on how to deal with how to reason about the complexity or the computational complexity of spanners. And for that, I want to talk about 3 ingredients of this theory. First is what are the proper complexity measures for spanners? In databases, we have data complexity where we fix the query, and we have combined complexity. What happens with the spanners? The picture is more involved. And 2 other things, enumeration complexity and the validity that I'll mention. So let's start with complexity measures for spanners. So in the world of database, we have 2 main reasons. There are also others, but like the 2 traditional measures are the combined complexity and the data complexity. Under combined complexity, we assume that the input for a query evaluation consists of both the query and the database. And then usually problems are hard, and you would say, okay, but this is rather confusing, or doesn't really capture a reality, because in reality the query is tiny and the database is huge. Then you really should distinguish between the 2. So the extreme way of distinguishing between the 2 is the data complexity, where you say the query is fixed, and I'm basically considering only the database as the input. And when you say something like queries, conjunctive queries, relational algebra, or computable in polynomial time, you mean that for every fixed query, there exists an algorithm that runs in polynomial time for that specific query. So this is the data complexity. Now, when you look at the spanners, we have a problem with both of these measures. We claim that they are not appropriate. So first, if we use the combined complexity, then basically it's very difficult to get outside of the hardness boundaries. Even one join query over binary relations is already something that is hard. So it won't get us far by talking about the combined complexity. But we felt like looking at the data complexity is somewhere cheating, or too much of a cheat compared to reality. And let me explain why it is a bigger cheat than in the database theory. But first, just let me get the more precise picture, or the picture in a more visual way. So this is our spanner, right? And it has like this is the input document. The spanner has the relational structure of the query. And instead of querying relations, it queries the atomic extractors, each of which is applied to the document. So, okay. Now, when you look at these regex formulas, they can be quite large. These are examples of regex formulas for very specific, very simple tasks. This is the date format of RFC, one of the RFCs, and this is the mailbox format. These are just regex formulas that that recognize the standard formats for these things. So very simple, but already hundreds of symbols. So if you look at data complexity and we say, okay, this can be fixed, and you have a polynomial with, I don't know, this length can be the degree of the polynomial, that's already taking the cheat quite far. All right, so we've been looking at this third, or we and others have been looking at this third notion of complexity, where instead of fixing nothing or fixing the entire query, you're fixing only the relational part of the query. Okay? So this is something called the extraction complexity. The relational part is fixed, like it's a join followed by an union followed by a projection. And the input consists of the text document along with all of these queries, regular expressions, or spanner automata that you push to the document or to the query as part of the input. Okay? So this is the extraction complexity. Here's another issue. If we allow the regex formula to be part of the input, then it might be the case that the output is just too large. Like, by the definition of the spanner, it extracts all the possible spans, and then the number of tuples can be actually exponential, just writing down the tuples. Now, this is a problem in terms of complexity, because we cannot say that a spanner that is assigned the task of producing an exponential number of tuples is intractable, because it is required to produce a large output. Just writing down the output is something that takes more than, say, polynomial time. For these kinds of cases, we are adopting the so-called output-sensitive complexity measures that allow you to measure the complexity of an algorithm or a query evaluation algorithm in terms of the size of both the input and the output. So this is not about spanners. This is a general theory of enumeration complexity. Okay? So here are kind of the standard definitions in enumeration complexity. These are the notions of tractability. The common one, or one of the most common ones, is polynomial total time, which says that the running time, the execution time, is polynomial in the combined size of the input and the output. Okay, so you have an algorithm. It can wait for a long time before it produces something. In the end, it produces stuff. And the total running time is a polynomial in the size of both. There is also one measure that's called incremental polynomial time, which means that the running time before the ith answer is polynomial in the input and also in I. So if you have many answers, then you can wait for a long time before you get the ith answer. But this time should be polynomial in I. Of course, you're not allowed to produce the same answer more than once. Okay, so you cannot just throw out some tuple again and again. And the strongest definition in this class of tractability notions is a polynomial delay, which means that you need to produce the output, and the time between every consecutive output items is polynomial only in the size of the input. That's called polynomial delay. Okay? And I can also think of other kind of delays, log delay, constant delay, with the same idea. All right? So these are notions of tractability for enumeration problem, for problems that are required or can, in the worst case, produce an exponential number of answers. Okay? And polynomial delay is stronger than incremental polynomial time, which is, in turn, stronger than polynomial total time. How do we prove hardness of enumeration? Well, one of the simplest ways of proving hardness is by showing that the emptiness problem is hard. So we have this problem of generating all of these answers, and I want to show that there is no algorithm that runs in polynomial delay or polynomial total time. So if I'm able to show that this emptiness problem is a hard problem, like NP-complete, then it shows also that there is no algorithm that terminates into polynomial total time. Okay, and so is the connection, is the statement clear? One wants me to repeat? Right, so why is it true? If I can show about a problem that just verifying or just answering the question of, is there at least one answer? If this problem is already hard, then there is no algorithm that terminates with polynomial total time. So it's a tricky question because this algorithm here, it can take exponential time. You cannot just run it and wait for it to terminate, because if it has an exponential number of answers, then it will take a long time for this algorithm to terminate.
Unless if you find a way to know that there is no solution without brute forcing all the possible solutions.
Yeah, but suppose that I don't. I just give you the algorithm. I'll tell you, hey, I have this algorithm that guarantees polynomial total time. And one comes and says, well, it makes no sense, because with this algorithm I can decide whether there is at least one answer. How would you do that? Well, the point is that if there are no answers, then we have the guarantee that the algorithm will run in polynomial time in the size of the input, and the output, which is the empty set, which means that the running time is polynomial only in the size of the input. So what do? I just let the algorithm run and open my watch, and after this polynomial time that I'm guaranteed, I stop the algorithm. I say, okay, if the algorithm returns something, then there's an answer. If it didn't, well, I know that there must be an answer. Otherwise, it would have terminated first. And of course, if it terminates ahead of time and says there are no answers, then I'm done. Right? So this is the trick. So why is it important? Because there will be some problems where I'll say, okay, the emptiness problem is hard. Then it excludes the possibility of efficient enumeration algorithms. All right. So very quick point. I've been mentioning these properties of functional. Every assignment or every parse tree or every run of the algorithm produces exactly one assignment to every variable. These are properties when we talk about computational complexity, we need to make sure that these do not add to the complexity of the problems. And basically this slide says, no worries. We can decide on the functionality of Regex formulas and spanner automata which is a decidable problem and even a polynomial time decidable problem. And also, if you start with Regex formulas, you can make a conversion to automata, spanner automata in linear time in the size of the spanner in the Regex formula. Okay, so basically the statement is no worries about this validity functionality testing. All right, so we're done with the three ingredients, and let's start talking about complexity results. So one complexity result is that if you look at the primitive extractors like Regex formulas, spanner automata, the answers can be computed with polynomial delay. This is under the combined complexity or the extraction complexity, which is the same because you have only one atomic extraction, the extractor that is given as part of the input. Now, the team of the Chileans in collaboration with Stein, they show that if you look at data complexity, where you fix the spanner, the Regex formula or the automaton, then the execution time is actually constant delay. You can enumerate with constant delay between the answers after a linear preprocessing. So it basically means that the time it takes to evaluate a spanner is the time that it takes to read the string and then just writing down the answers. It's quite efficient, but it assumes data complexity. Like the times here can be exponential in the size of the representation in the automaton of the Regex formula. And then there was a result that kind of gave us the best of both, an algorithm by Morelli et al. Showing, well, they gave one algorithm that enumerates with the same complexity here, linear preprocessing and constant delay, but now all of the times are actually polynomial in the size of the automaton of the query, which means that the same algorithm is both polynomial delay in combined complexity and constant delay in data complexity. Okay? So now, if we have these classes of primitive extractors, Regex formula, spanner automata, string equality, they are all computable with polynomial delay. What happens when we're adding the algebra? Well, here when you do algorithmic design, you have two approaches of how to attack this problem. How do I come up with an algorithm for evaluating, say, the join of two spanners? Okay, yeah. So there is what we call the canonical approach. Just do what the spanner does. Evaluate alpha. So the input is a document D, and we evaluate alpha over D. Evaluate beta over D. We get two relations, and we just send them to a relational query engine to compute the result. Okay, this is the canonical approach. There is another approach. Any guess of what it will be? Well, there is the compilation approach, which is don't touch a document. First compile alpha and beta into one automaton, one representation that corresponds to the join. Only then evaluate the document over this compiled representation. Okay? And the interesting thing here is that each of these approaches gives you like a different set of tractable cases, and each has its own problem. Like with the canonical approach, it might be the case that these intermediate results that you're producing are large, actually exponentially larger than the size of the final output. This is one of the questions in the challenge that that I'll describe this evening, is showing that indeed it might be the case that these intermediate results are exponentially larger. And again, because these Regex formulas can be complex and they can have many variables. The problem with the compilation approach is that, well, this compiled object can be large. In the case of joins, we know how large that is, well, at least, well, it can be quadratic, at most quadratic, but in the case of other operators, it can be even more than that. Okay, so here are some results that you immediately get from the compilation result. Well, if you have, if you can actually evaluate all of your atomic spanners in polynomial time, and you produce a problem where the query, your relational query, belongs to some tractable fragment, like polynomial delay, cyclic queries, and so on, or cyclic joins, then you get that you have a tractable spanner. And the interesting thing is that both of these conditions are crucial. In particular, it may be the case that each of the atomic spanners takes constant time to evaluate, but then the query is so complex that the entire problem is actually NP-complete. Okay, so it's if just the spanners are easy to compute, but the query is complex, the structured query, the relational query is complex, then you have a problem. It may also be the case that your structured query is easy to compute, tractable, like a cyclic join or a path join. In the relational world, it's tractable. But here, it becomes intractable. Again, because these spanners, these Regex formulas that you're using, might produce very large outputs that you cannot actually instantiate. Okay, so both of these conditions are important. What do you get through the compilation approach? Well, from the compilation approach, we can conclude that every positive relational algebra query can be evaluated with polynomial delay when applied to Regex formulas or spanner automata. And the reason is that we can compile every positive relational algebra query into a single automaton. Large automaton, but the size of the automaton is kind of exponential just in the number of relational operators that we have. So this is extraction complexity, not combined complexity. Okay? And it holds for Regex formulas and automata. And actually, even if you give me, in addition to all of these complex automata, also some black box functions. Like, I don't know how this function is implemented. It can be whatever statistical or deep network model that you have. I only have the guarantee that it computes all of the extraction in polynomial time. Then I can actually incorporate it into the computation. And this is a question, this is one of the challenge questions, the question I was referring to previously. Okay, so this is quite a general tractability result. All right, so in terms of our general picture, we get that with the positive relational algebra, everything is polynomial time. Well, the obvious question is, why positive? What happens with difference, right? What happens with the relational algebra? And here we have bad news. It doesn't go through the difference. The following problem is an NP-complete problem. I'm giving you a document, D, and two Regex formulas, alpha and beta. The question is the emptiness problem, the non-emptiness problem of the difference. Is it the case that alpha D minus beta D has at least one answer? And this problem is actually NP hard. Again, what is the difficulty? Why not just computing alpha D and then computing beta D and taking the difference? It is because every intermediate result can be very large. Okay, so if it was a join, then we could do it in polynomial delay. But the difference is actually hard. Okay, so as we said previously, this means that we don't have evaluation in polynomial total time or polynomial delay. And basically, this completes the picture of the relational queries. If if you apply array to equal string quality, then this is all easy. But when you apply it to Regex formulas or to spanner automata, the problem, the extraction complexity is intractable. It is NP-hard. Okay? Questions so far? Okay. Let's talk about aggregate queries. What do I mean by aggregate queries? Queries that basically do count or sum, the standard aggregate queries, average, min, max, on top of spanners. Well, first question is, what is the meaning of that? Like I can, you can imagine what count over spanners mean. Just how many answers do I have? How many tuples? What is sum? Where are the numbers coming from? Okay? So here, I will make the assumption that we have some function that goes into the document and translates spans into numbers. And this can be something that is quite natural, right? You have some function that goes into the document and finds patterns of numbers, like 25. The word in English, 25, maps to 25. The number tree maps, or the character tree becomes the number tree. And 650 out of these characters, and so on. Okay, so you can imagine that you have some process that goes into the document and extracts numbers, gives you a mapping from spans to numbers. All right, and with this assumption, we can assume that we have this function num that gets as input a span and gives you as output a number. And then we can define what it means for aggregate. What is the semantics of the aggregate queries? Like sum over the variable x of the spanner alpha for the document D is sum over all of the tuples of alpha D of the number that the x span of T is mapped to. Num T x. Right, and then average is just sum divided by count. Max is the max number, maximum number, and min. Right? Well, we also need some tools from complexity here to reason about these numbers, these problems. Because, well, when we talked about decision problems, we had these standard classes of polynomial time, NP complete, and so on. And then at some point we needed to talk about enumeration problems, and we needed some other classes like polynomial delay, polynomial total time, and so on. These are a different type of problem. These are problems that generate numbers, okay? And we need to use the proper complexity theory for that. So generally we're looking at function, the computation of functions fx given the input x. So the standard classes are set of p, fp, functions computable in polynomial time. And the standard way, the standard intractable class in this kind of problems is Sharpie. Sharpie is the class of all the problems that are, think of them as computationally equivalent to counting the number of satisfying assignment to a hard formula, a CNF formula, okay? So, it is considered intractable to determine whether there's at least one satisfying assignment of a CNF formula. Sharpie says, okay, give me the exact number of satisfying assignments to this formula. So, for example, this problem is computationally equivalent to counting the number of satisfying assignments of a DNF formula. Although satisfiability of DNF is very easy, counting the number of assignments is the same as counting the number of assignments of our CNF. All right. Well, then we have the following results. If you're looking at the data complexity, well, everything is in FP, but when you look at the combined or the extraction complexity, which is the same as combined complexity in this case, then max and min are functions that you can compute in polynomial time, but all of the count, sum, and average become sharply hard. Okay, so it seems like a very negative, pessimistic picture, but in fact, we can get very good approximations with provable guarantees. So what are the approximations in this case? Well, we are adopting this standard concept of fully polynomial time randomized approximation scheme. This is an algorithm that you use instead of computing the function f. Use this algorithm A, which is allowed to be randomized. And the input of f is some input x, so the input of A is an input x of f, plus some small number epsilon. This algorithm A is required to terminate in polynomial time, not only in the size of x, but also in 1 over epsilon. That's the fully polynomial time scheme part. And it has the following guarantee. The number that it produces is a multiplicative approximation of f. It is within 1 plus epsilon times f to fx over 1 plus epsilon, okay? And since this is a randomized algorithm, then this should happen with some high probability. Okay, and this 0.9 is just an arbitrary choice. It can be amplified to any 1 minus delta. All right, so this is the definition of an efficient, or one of the common definitions of an efficient approximation algorithm. And what Arenas et al. Have shown, this is actually the part of the best paper of PODS 2019, last PODS, is that the count problem for spanners or Regex formulas, spanner automata, has an f plus. Okay, you can have an approximation for count with all of the goodness of f plus. With that, we can actually show that this generalizes to the tractability or to the approximation of sum and average. Okay, but only if you have non-negative numbers. If you have negative numbers, then this doesn't apply. We can actually show that it isn't possible with negative numbers. But with positive numbers or non-negative numbers, you have this picture. Okay, so generally the picture is fairly optimistic. Some functions you have they are in polynomial time. Some other functions have very efficient or algorithms that are in theory very efficient and precise. All right? Questions so far? Yes, Dan.
So, in all of these cases, you actually have to either in counting or they have this published and completed set. But even in global relational databases, pretty evaluations, including case already empty out. Yet, databases do it every day. And that's actually because we know, actually from the theory, that what's being asked in that is not the hard cases for which actually the problems are hard. I was wondering whether you have any intuition whether here actually you could expect to see something similar in practice, in the sense that most people are asking is actually quite, trainings are quite simple, or do you expect actually the situation here is worse?
Yeah. So, good question. So, question is what are the realistic assumptions, whether there are some realistic assumptions that can help us. And again, we can look at this problem as having three components: the relational structure, and the extractors, and the input document. Now, we did show that with only the assumption of a cyclicity or being a path query, that doesn't take you outside of NP completeness. Okay, in the worst case. Okay, if you're not making any assumption over the query, but you're making very strong assumptions over the extractors, then this is also not enough in the worst case. So what you need to do is to find properties that are kind of applied to both of them. Some properties of both the structured part and the extraction part. And this is not something that we've been doing. But I know that the Parisian group of Antoine are now working on, well, we've been starting to build some benchmarks for Regex formulas, which you're familiar with, but now Amarillo et al. Are constructing a benchmark of Regex formulas, and we might get some insights there. But as far as I know, there are no clear assumptions that were distinguished to be such that provide us some tractability results. Yeah. Any other questions? All right. So now I'll skip as I expected, I'll skip the part where I talk about generalizations. Just, they're in the slides, and the slides are online. And but basically, I talk about incomplete the generalization into incompleteness models, and then a generalization that talks about a structure of a document, documents rather than just one document at a time. This is a work that started with Stein, collaborating with my students. And another generalization are like weighted spanners or annotating spanners. That is actually a very recent work, and we just got something published on archive today. Okay, so I'm not going to talk about these topics, and I'm going to skip to the next part, where I basically talk about several aspects that are, well, two of them are very recent research topics that kind of reach out to other areas and or are very initial and require some further research. So this kind of gives research directions. And these aspects are distribution, inconsistency, and explanations of queries. Okay, let me start with distribution. So here, we're basically thinking of the following query planning for spanner. So, in the general case, you have a document, you have a spanner, and the spanner produces some table out of this document. Now you can think of the situation where you have some split of this document into some logical fragments, spans, like sentences, paragraphs, or if it's like a log of an HTTP engine, web engine, then you have a split into the different messages, requests, and so on. And then what, from my experience, what people do in practice when they have these kinds of problems and the document is like very long, or say too long for the task at hand, maybe, which say can be an online task. They realize that a lot of what they can do, or a lot of what the spanner P needs to do on a document, can be done, say, on every sentence independently, or on every paragraph independently. And so, to begin with, they evaluate this spanner on each of these chunks independently. And you can use all of the parallelism, and nowadays you have a lot of parallelism power in our machines. And we combine the results of all of the cores, and the question is, did you get the exact same result? So at IBM, we essentially used to do it manually. We would observe that this is a problem that is easily parallelizable, or much of it can be easily parallelizable, and we would just evaluate it on the different chunks. Question that we've asked here is whether this is something that can be automated. I give you a spanner, and there is some way of splitting the document. I'll make it more formal in the next slide. And is it true that you can evaluate the original spanner by evaluating it on every chunk independently? And this is this work was published in the last pods this year. Okay, and so the motivation is, of course, performance and distributed query planning, but there are other motivations to this problem, like the motivation of debugging. Suppose that I'm writing some spanner, and then the system goes and says, well, this spanner would not give me the same answers if I executed on each paragraph independently. Now, is it something that I deliberately want? Do I have like cross-paragraph dependencies, or just a mistake? Okay, in many cases, I'm extracting unrelated stuff because I wasn't careful enough to not go outside of the boundaries of the paragraph. And another motivation is incremental maintenance. Suppose that you have like a long document like Wikipedia, where one goes and changes one word somewhere in the big document. Okay, so if you want to your spanner output to be up to date, in principle you need to evaluate it from the very beginning. But if you know that your spanner is splittable by sentences or by paragraphs, then you know that basically you need to do very little in order to keep your output up to date, or at least a major part of the computation is already almost up to date, and you just need to compute the delta and evaluate the final result. Okay, so now we can actually get a formal definition with our spanner formalism. A splitter is a unary spanner S. It produces a tuple, a table with one attribute. And a spanner P is correctly split by the splitter S if it is the case that for every document D, we have this equality. Applying P to D is the same as the union of applying P to the S chunk of D, where S is a span that belongs to SD. Okay, so we're going over all of the spans that we get from the splitter. We apply P to the corresponding string, and that's it. But we also need to align these spans, because if I have a span extracted from chunk number 1000, then the second symbol is actually the n+2 symbol. Okay, so we need to have this alignment. Okay, but this gives us a very natural definition, and you can extend this problem and say, well, is it necessarily the same P and so on? Maybe this should be, there's another P prime that I can evaluate and get this equality. Okay, so this is just the definition and the paper has some analysis, like what is the complexity of determining whether P is correctly split by S, and so on. Okay, so, well, in the Potts paper, it's really a framework paper that sets out a new problem, and research directions are both theoretical and practical, seeing, for example, how much we can actually detect these cases in real-life problems. Another topic is inconsistency. And this is some work that we've, another collaboration with Stein, and think of it as follows. So the extractors might make inconsistent or erroneous extraction, but not just erroneous, that extractions that have inside conflicts. So a typical example is that we have an extractor saying, well, here I have a person, Martin Luther King Jr. extracted, and another one would say, hey, I have another person here, but you see that they overlap, and another extractor will come and say, well, this is all part of one big address. So in the end of the day, you have three extractors giving you three entities with overlapping spans. And in many cases, in many instantiations of these systems, this is considered a conflict, something to be avoided. So now you can say, okay, we should have probably written these extractors or spanners in a way that avoids these conflicts to begin with. Well, it's not that easy. It actually can make programs very complicated. So instead of requiring the developers to write programs in a way, where you don't have these conflicts, these undesired overlaps, they provide mechanisms to clean the extraction after you extract parts with overlaps. And this comes in different ways, consolidators, controls in a gate. It even goes back to the way POSIX defined the semantics of capture variables in the regular expressions. They do not give you all of the matches, but just some of the matches. Which matches? Well, this is some policy that needs to be properly, formally defined. Right? And so you remember I showed you this picture of the system T snapshot of the code, and there is this rule here that says, well, from the person-all relation, throw away any person such that the name is strictly contained in the name of another person. Okay? This is what this consolidator is doing. In the Snorkel tutorial, you can actually find this rule being used in the person matcher. Person matcher with the parameter longest match only is equal to true. Okay, so it's also one of the toolkit for writing the rules. In the gate system, they've been providing developers with a collection of these conflict resolution or cleaning operators. So you can define what is the semantics that you want to use for the cleaning. So here we have a document, sequence 1, 2, 3, 4, 5, and sequence 1, 2, and the regex extracts all of the spans that are 2 or more digits. Okay, so the all semantics will give you all of the extracted spans, and the one semantics will stop the first time it found one match, and the brain will allow for some overlaps, but only with prefixes and so on. So also when you look at the documentation of what these conflict resolvers do, it's not very easy to understand, because they talk about the algorithmic side, how the matcher is stopping at some point and then starting in the next point and so on. Okay, so what did we do? With the system T group, we were asked the question of, can we come up with some formalism, some logical way of specifying these conflict resolvers in a way that is kind of clearer, more principles, and more general. Like the current consolidators are kind of, well, they are a kind of ad hoc set that is predefined without control of the developers. So we propose this framework based on the spanners where you can state things like, well, you have two kind of statements. Which tuples are in conflict? Like if x and y are overlapping spans, then it cannot be the case that x is a person and say y is a location. All right? And whatever comes to mind or matches the logic, like if x and y are separated by the word or, then it cannot be the case that one is a person and one is a location. Okay, so it's just a constraint language. And you can also, and you need also, to specify preferences. You say things like, if y strictly contains x, if the span y strictly contains the span x, then person y is preferred to person x. Or it is the case that I always prefer the location extraction to the person extraction. Why? Because I trust my location extractor better. Okay, so it doesn't mean that we throw away all of these person x. It just means that if we have a conflict, then we prefer one of the other. But we also need to define what this means. Okay, so the first type of rules is what we call in databases denial constraints. And the other type is just a preference among tuples. Okay? And there's actually a framework in database or in database theory that nicely captures what's going on. And this is the framework of prioritized repairs by Staroko, Komitsky, and Marcinkowski. Okay? And there, basically, the idea is that your database may have conflicts, but it also has preferences among tuples. So a database consists of a set of facts, right, the database tuples, a set of denial constraints, like functional dependencies, and some preference relation. And then the main question here is, well, you have preferences between the tuples. How does that translate into preference between subsets? This is what we want in the end. What is the best subset? Okay? And there are several different definitions. Like one subset improves upon another subset, and these are all consistent subsets, if, say, for every distinct tuple of the left one, there is a better distinct tuple of the better one. Okay, this is a global improvement. Another definition is Pareto improvement. The right one is better if there is one tuple that is better than all of the tuples that are distinct, that are unique only to this subset. They are on the left, but not on the right. Okay? And then based on these improvement definitions, you can define what it means to be a globally optimal or an optimal consistent subset. It is globally optimal if it doesn't have a global improvement. Pareto optimal if it doesn't have a Pareto improvement. You can also think of a third one, which is the greedy solution, what you would get by finding the best tuple and then the next best tuple that is consistent with what you've selected so far, and so on. Okay, so this gives you like tree semantics, and the research around that has been on all sorts of problems like consistent query answering, what are the answers that are true in every optimal repair, and repair checking is a given subset an optimal repair, and counting and enumeration. Or is it the case that the preferences define exactly one optimal repair? Like they have sufficient preferences to fully clean the data without ambiguity. Okay? So what we've shown in that work is that basically this framework properly captures the cleaning operators, the consolidators that you have in system T, the gate system, the POSIX formalism. They're all captured in this framework of prioritized repairs. And we studied all sorts of questions like, do the rules make sense? Like, can they introduce some cycles, right? Or is it guaranteed that the rules are giving you one repair or one best subset unambiguously? Okay? Or do they add expressive power? If you have a program and you apply these consolidators, does it enhance your expressiveness? Does it increase your expressive power? Or it is not, and it is there, just for convenience, or you get better algorithms and so on. So we got some I think, surprising results there. Last thing, which I'll go through quickly, but I find quite interesting. This is really just a direction for research for future research. Okay, but with some background. So explanations. Here we're talking about these kinds of workflows, this machine learning pipeline, which is very common, where you have your data, and part of it is like the text documents. You're analyzing this document, you're applying queries to this database in order to extract features. From these features are fed into some machine learning algorithm, which makes a prediction. And then you're asking the question of, why did I get the prediction that I got? So if you look at this pipeline, the explanation can consist of explanations of the specific individual errors here, right? If you look at what people have done in machine learning, then they did things like, what is the most influential feature value on the result of the prediction? Okay, so it goes by sensitivity analysis, like how much fluctuation would you have if you change this value, or Taylor decomposition, more of an analytical explanation, and attention models in deep networks, and also recently the Shapley values, okay, which is something, some concept from game theory. I'll talk about it next. Okay, so now this explains which features were most influential. But now, looking at a specific feature, it came from the database. Which database tuples or facts were the most influential? Are the explanations for the feature that I got? And the database community has been developing several of these concepts of tracking down the tuples that are responsible, or quantifying the responsibility of tuples to query answers, which are features in this pipeline. Okay, so the Y provenance, responsibility, and causality. And recently, we've been doing some work on the Shapley values. Okay, so these Shapley values, they're kind of, we actually did it independently without being aware of how it is done in machine learning. And the Shapley value comes from game theory. And this is a general idea of, if you have a coalition of people doing something for that in the end results in some profit, how do you split the profit? How do you divide the profit between the players? Now, it may be the case that you cannot assign a clear portion to each of the actors, each of the players in the coalition. But then Shapley in 53 proposed one function that is very general, and also some theory that explains that under some desired, the assumption of the desired properties, this is the very unique single function that exists. Okay, and it's been used in many fields. And the point is very simple. You have a set of A of players, and you have a wealth function that gives every subset like a value. Okay, every subset gets some value, which can be whatever you want. And And the question is how to share the wealth between the players. So the short answer is that there is a, or the complex answer is that there is a formula here, which or basically some division between factorials and whatever. But here's the semantics of it, very simple. So I'm trying to quantify the responsibility of this red person to the game, to the coalition, to the wealth. So I'm doing the following game. I'm selecting people one by one, randomly, without replacement. Okay? And then at some point, I'm selecting the red guy. When this red one has been added, there's a change in the wealth function. It used to be 12 just before this person has been added, and suddenly it is 17. Okay, so the contribution is 5. Shapley value is simply the expected delta in a random permutation. What is the expected value that this person adds when I take a random permutation? It's very simple, very general, and has some, as I said, some nice theoretical properties. And how is it related to what we're doing here? So the wealth function can be the prediction itself or the score of the classifier. And then who are the players? Well, the players can be the feature values. And then you say, okay, how much is every feature value contributing to the coalition? I'm not being precise here, but this is the essence. Or the database tuples. In the work that we've been doing, we've been basically looking at the database tuples as the players and say the query or the aggregate query as the wealth function. And then we could quantify how much each tuple of the database or how much each of the authors was responsible, say, to the overall number of citations that a department has. Okay? And then what we didn't do, and I think is very natural, and I'm, again, opening it for future research, is you could also view your players as your documents or individual spans, like sentences or paragraphs. And then you can find these sentences or paragraphs that best explain the result of the prediction. And that might give you a strong clue on why the system thought that the prediction should be positive or negative. And this I leave like that. And this is just a summary of the entire lectures. I talk about the paradigms of IE. I talk about the different roles that they have, the document spanners as the theoretical framework that we've been using. I gave some results about expressiveness and complexity, and the different tasks that have been studied. And there's much more to do, including the practical direction of taking this theory and these algorithms that are like fundamentally changing the theoretical complexity and making them game-changing, translating them to game-changing speed-ups of practical tasks. And that will be all. Thank you very much.